Have you ever wondered what lies at the center of the universe? Is there a core to everything we see in the cosmos, or is the idea of a center just an illusion? Scientists have long debated whether there's a specific point where the universe began, or if it stretches endlessly in all directions. Join me as we explore the theories about the universe's origins, what exists at its center, if anything, and how our understanding of space could change the way we think about everything around us. The cosmic axis of evil, a mysterious alignment in the universe. In order to find the answer to these questions, we need to understand the mysterious alignment of the universe. You see, in the early 2000s, something strange emerged from the most detailed maps of the cosmic microwave background, CMB, the ancient light left over from the Big Bang. This light is a snapshot of the universe when it was only 380,000 years old, a glowing afterglow spread evenly across the sky. The CMB is an essential tool for cosmologists because it holds the key to understanding how the universe began and evolved. For decades, scientists believed this background radiation was almost perfectly uniform, with only tiny fluctuations that represented the seeds of galaxies and stars. But upon closer examination, an unexpected alignment was found, something that has come to be known as the cosmic axis of evil. The discovery of this mysterious axis didn't fit neatly into the framework of an isotropic universe. The name itself, axis of evil, comes from the fact that this alignment seemed to go against the randomness and uniformity that were expected. It felt like a cosmic anomaly. The axis of evil refers to a large-scale alignment of certain features in the CMB, specifically patterns that shouldn't have any particular orientation. Yet, this axis suggests that these patterns are strangely aligned in a specific direction across the universe. It was as if the universe, instead of being entirely uniform, had a preferred direction, a finding that doesn't easily sit with the idea of an evenly expanding universe. So what's going on here? Could this alignment be telling us something new about the nature of the cosmos? There are several potential explanations, ranging from more straightforward observational issues to the more mind-bending possibility of unknown forces or cosmic structures influencing the universe on a large scale. Some scientists argue that the cosmic axis of evil could be the result of observational bias or errors in the way the CMB data has been collected. The CMB maps are made by space telescopes, which, despite being incredibly advanced, are still subject to limitations. Perhaps the alignment is simply a coincidence, an artifact of the way the data was processed, or a quirk in the instruments used to measure the CMB. If that were the case, further observations and refinements to the data might make the alignment disappear. But the axis of evil has persisted through multiple data sets and observations, raising the possibility that it's not just an error. Could there be something more profound going on? Some researchers have proposed that this alignment could be caused by large-scale cosmic structures that we haven't yet fully understood. It's possible that massive structures like clusters of galaxies or even more exotic forms of matter could be exerting a subtle influence on the shape of the universe. These structures could be bending or warping space in such a way that the CMB appears aligned in specific directions. Another explanation might involve dark energy or dark matter, mysterious components of the universe that we still don't fully understand. Dark matter, which makes up about 27% of the universe, doesn't emit light or radiation, so it's invisible to us, but we know it's there because of its gravitational effects. Dark energy, on the other hand, is thought to be driving the accelerated expansion of the universe. Could these unseen forces be playing a role in shaping the alignment of the CMB? It's possible that the cosmic axis of evil might be a sign that these mysterious substances are influencing the universe in ways we've only begun to grasp. There are also more exotic theories. Some physicists have speculated that the cosmic axis of evil might hint at a deeper underlying structure or force that we don't yet fully understand. One idea is that the axis could be evidence of a violation of cosmic isotropy, the principle that the universe is the same in all directions. If this principle is not entirely correct, it would fundamentally change our understanding of the universe's geometry. Perhaps the universe is not as symmetrical as we thought. This could open the door to new theories about the shape and structure of space-time itself, including the possibility that our universe is part of a much larger, more complex multiverse. This idea, while speculative, has captured the imagination of some cosmologists. Could the cosmic axis of evil be a sign that our universe is influenced by forces beyond our observable reality? If we are indeed part of a multiverse where different universes have different physical laws or structures, then it's conceivable that the alignment we're seeing in the CMB could be a reflection of interactions with neighboring universes or higher dimensional phenomena. While this is still very much in the realm of theory, it points to just how much we have yet to understand about the cosmos. What makes the cosmic axis of evil so intriguing is the impact it could have on cosmology itself. For decades, the idea that the universe is isotropic, that it looks the same in all directions, has been a foundational assumption in cosmology. If the axis is real and not just an observational error, it could mean that this assumption needs to be revised. A universe with a preferred direction would challenge some of the most basic principles of modern cosmology, forcing us to rethink how the universe evolved and how it continues to expand. This anomaly in the CMB data also highlights how much of the universe remains mysterious. Even though we've made incredible strides in understanding the cosmos, there are still deep, unresolved questions that could upend our current models. The cosmic axis of evil may be one of those questions, pointing to an unseen pattern or structure that influences the entire universe. If it's real, this alignment could lead to new discoveries about the universe's origins, its ultimate fate, and the forces that shape everything we know. The cosmic axis of evil leaves us with a sense of mystery, a clue that the universe might be hiding something about its fundamental nature that we don't fully understand. This strange alignment challenges our assumptions about the uniformity and randomness of the cosmos. But beyond this anomaly, there are other ways the universe might be structured that could tell us even more about how everything works on the largest scales. While the idea of a cosmic center might be tempting, the overwhelming evidence from our observations suggests the universe doesn't have one. The expansion of space continues everywhere, stretching galaxies apart without any single point from which everything began. This ties into another fundamental question in cosmology: the shape of the universe itself. If we imagine the universe as a vast, expanding entity, we naturally wonder about its overall form. Does it stretch out infinitely? Does it curve back on itself like the surface of a sphere? Or is it something else entirely? The shape of the universe. Understanding the universe's shape requires us to dive deep into the geometry of space itself and how it interacts with gravity, energy, and matter. There are three primary possibilities for the universe's overall shape: flat, open, and closed. Each of these shapes tells us something different about how the universe works and what might happen to it in the future. To begin, we need to think about the basic geometry of space. When cosmologists talk about the universe being flat, open, or closed, they're referring to how space behaves on the largest possible scales. A flat universe is one where parallel lines remain parallel forever, like on a flat piece of paper. In this model, space doesn't curve in on itself, and the overall geometry is Euclidean, meaning the rules of geometry we learn in school apply. A closed universe is one where space is curved like the surface of a sphere. In this model, if you travel far enough in one direction, you would eventually come back to your starting point, just like walking around the surface of the Earth. Lastly, an open universe is one where space curves outward, like a saddle, and parallel lines eventually diverge. In an open universe, space continues expanding forever, and the further you travel, the more spread out things become. To figure out which of these models best describes our universe, once again we have to turn back to the cosmic microwave background. By studying the patterns in this ancient light, cosmologists can measure the curvature of space. If the universe is flat, light from distant galaxies and the CMB should travel in straight lines. But if the universe is curved, that light will bend in predictable ways, depending on whether the universe is open or closed. One of the key ways scientists measure the universe's curvature is by looking at the size of certain features in the CMB. These features are fluctuations in temperature that represent the seeds of galaxies and other cosmic structures. In a flat universe, these fluctuations appear at a specific size. But if the universe is curved, the apparent size of these features changes, larger in a closed universe, smaller in an open one. By carefully analyzing the CMB, cosmologists have been able to measure the curvature of space with incredible precision. So, what do the measurements tell us? Based on the most recent data, it appears that the universe is very close to flat. This means that, on the largest scales, space doesn't curve much at all. It's not perfectly flat, but it's close enough that, for all practical purposes, we can think of it as flat. This flatness has some important implications for the future of the universe. In a flat universe, space continues expanding forever, but at a slower and slower rate. Eventually, galaxies will drift so far apart that they're no longer visible to one another, but the universe won't collapse back in on itself. In a closed universe, by contrast, the expansion would eventually slow down, stop, and reverse. This would lead to a scenario known as the Big Crunch, where all matter and energy in the universe would collapse back into a single point, similar to how it all started with the Big Bang. In this model, the universe is like a balloon that expands to a certain point and then deflates. While the closed universe scenario is interesting, the current evidence doesn't support it. The data from the CMB and other measurements suggest that our universe is not curved enough to collapse in on itself. An open universe, on the other hand, would continue expanding forever, but at an accelerating rate. In this model, space would stretch so much that galaxies, stars, and eventually even atoms would be ripped apart by the relentless expansion. This scenario is sometimes called the Big Freeze or heat death, where the universe becomes so stretched out that all matter is spread thin, and no new stars or galaxies can form. While this is a possible outcome, the data again suggests that the universe is much closer to flat than open. But what about the idea of a center? In a flat or open universe, there is no center, just like in the expanding balloon analogy. Every point in the universe is moving away from every other point, but no single point is special. If you were to pick any galaxy in the universe, it would look like all the other galaxies were moving away from you. This is a consequence of the uniform expansion of space. In a closed universe, however, the geometry is different. A closed universe curves in on itself, like the surface of a sphere, and theoretically this could imply some kind of central point. But this center wouldn't be located in our three-dimensional space. It would exist in a higher dimension, outside of what we can observe. This makes the idea of a central point in a closed universe more theoretical than practical. The fact that we live in a universe that appears to be very close to flat also supports the idea that the universe is infinite. In a flat universe, space extends forever in all directions, without looping back on itself. This means there's no edge to the universe and no center. While we can only observe a small portion of the universe, the observable universe, the actual size of the universe is likely much larger, possibly infinite. This has profound implications for our understanding of space and time. If the universe is infinite, there's no central point or edge, and the expansion we see is just part of a much larger, never-ending process. Hypervelocity stars, rogue stars, fleeing from cosmic forces. Hypervelocity stars are a remarkable and rare phenomenon, captivating astronomers because of the clues they offer about the universe's most extreme environments. Unlike the majority of stars that follow predictable orbits within galaxies, these rogue stars are ejected at such incredible velocities that they are flung beyond the gravitational grasp of their home galaxy, traveling alone through intergalactic space. Their existence raises fascinating questions about how they're accelerated to such speeds and what they can teach us about the hidden forces and dynamics at play in galaxies, especially near their most dangerous inhabitants, supermassive black holes. The discovery of the first hypervelocity star came in 2005 when scientists stumbled upon a star traveling so fast that it would eventually escape the Milky Way's gravitational pull entirely. This star, HV1, was found to be moving at over 1.5 million miles per hour, a velocity far greater than what would be expected from a star bound by the galaxy's normal gravitational forces. This revelation opened up new avenues of research into what could possibly accelerate stars to such extreme speeds. One of the key theories explaining the existence of hypervelocity stars is rooted in their interaction with supermassive black holes, the enormous black holes that reside at the centers of most galaxies. Our own galaxy, the Milky Way, harbors one of these titanic black holes known as Sagittarius A, which has a mass about 4 million times that of our Sun. When a star comes too close to a supermassive black hole, particularly if it's part of a binary star system, dramatic gravitational interactions can occur. A binary star system is a pair of stars orbiting each other. If such a system drifts too close to a supermassive black hole, one of the stars can be pulled into the black hole, while the other star is slingshotted outwards at tremendous speeds. This process, known as the Hill's mechanism, is a type of gravitational slingshot effect. The energy from the interaction propels the remaining star outward with enough velocity to break free from the galaxy's gravitational pull entirely, sending it on a journey through the cosmos at breakneck speed. It's an extreme example of how supermassive black holes, typically known for their ability to trap everything, including light, can also have the opposite effect, flinging objects away at unimaginable speeds. The Milky Way's central black hole is one of the primary suspects for the origin of hypervelocity stars in our galaxy. The extreme gravitational forces near Sagittarius A** are capable of disrupting star systems and ejecting stars. When astronomers discovered hypervelocity stars like S5HVS1, one of the fastest stars ever detected, traveling at over 3.7 million miles per hour, they immediately suspected it had originated near Sagittarius A*. By tracing its trajectory back to the galactic center, scientists were able to strengthen this theory, confirming that these stars are often born near the chaotic heart of galaxies. However, binary interactions with black holes aren't the only way hypervelocity stars are born. Another possibility is through stellar collisions or interactions with other stars in dense star clusters. In regions of space densely packed with stars, such as the centers of globular clusters or near the cores of galaxies, close encounters between stars can also eject stars at high velocities. The gravitational tug-of-war in such crowded environments can occasionally fling stars outward, although the velocities achieved in these scenarios are usually lower than those produced by interactions with supermassive black holes. Interestingly, there's another lesser-known mechanism that can produce hypervelocity stars: supernova explosions in binary systems. If one star in a binary system undergoes a supernova explosion, the blast can propel the surviving companion star out of its orbit and into space at incredible speeds. The shockwave from the supernova, combined with the sudden loss of mass in the system, can impart enough energy to the companion star to send it racing away from its original location. While this process typically doesn't generate velocities as extreme as those seen in black hole interactions, it's still a viable way of creating hypervelocity stars. While these mechanisms explain how hypervelocity stars are ejected, studying these stars also offers a unique opportunity to investigate the extreme environments from which they come. In particular, hypervelocity stars act as probes of the supermassive black holes that ejected them. Since it's difficult to observe supermassive black holes directly, especially through the dense dust and gas that often surrounds them, hypervelocity stars provide an indirect way to study these cosmic behemoths. By tracking the paths and speeds of hypervelocity stars, astronomers can gain insights into the mass and behavior of the black holes that slingshotted them into space. For example, the speed of a hypervelocity star can tell astronomers how close the star came to the black hole during its ejection. The faster the star, the closer it must have passed to the black hole. By studying multiple hypervelocity stars, scientists can map the gravitational influence of the black hole and learn more about its surroundings. This information helps to paint a more detailed picture of what's happening in the dense, energetic environments around galactic centers, areas that are typically shrouded in mystery. Beyond their relevance to black holes, hypervelocity stars also provide insight into the gravitational landscape of the universe. Once these stars are ejected from their home galaxies, they travel through intergalactic space, free from the gravitational bonds of any galaxy. This makes them excellent test subjects for studying the distribution of dark matter and other large-scale cosmic structures. As hypervelocity stars pass through different regions of space, they are influenced by the gravitational pull of dark matter and other galaxies. By tracking their paths, astronomers can glean information about the unseen forces at work in intergalactic space, helping to refine our models of how matter is distributed throughout the universe. Another fascinating aspect of hypervelocity stars is the potential for even more extreme cases where entire star clusters are ejected from galaxies. While individual hypervelocity stars are rare, there is evidence to suggest that in galaxy mergers, when two galaxies collide, entire star clusters could be thrown out into space at high speeds. These hypervelocity clusters, if they exist, would be even rarer than individual hypervelocity stars. But they would provide further insights into the dynamics of galaxy collisions and the formation of large-scale cosmic structures. Moreover, studying hypervelocity stars in other galaxies may reveal more about whether these phenomena are common across the universe or unique to certain types of galaxies. In some cases, the sheer number of hypervelocity stars in a galaxy could point to an especially active or disruptive galactic core. For instance, galaxies with more frequent black hole mergers or more chaotic central regions might eject more stars than more stable galaxies. By comparing hypervelocity star populations in different galaxies, scientists can gain clues about the activity levels in various galactic environments. While much of the focus on hypervelocity stars revolves around their origins and their utility as probes of galactic dynamics, there's also an intriguing possibility. Could hypervelocity planets exist? If a hypervelocity star has planets orbiting it, those planets might be dragged along for the ride, carried into intergalactic space. Such planets, if they exist, would be nearly impossible to detect with current technology. But the idea raises fascinating possibilities about what kinds of worlds might be out there, far beyond the gravitational influence of any galaxy, traveling alone through the vast, empty reaches of intergalactic space. Primordial black holes, ancient giants at the universe's core. Primordial black holes represent one of the most ancient and intriguing possibilities in cosmology. These black holes, unlike the ones we know that form from the collapse of massive stars, could have been born in the very first moments after the Big Bang. Their potential role in shaping the universe is fascinating because they might provide answers to some of the biggest questions in astrophysics, from the nature of dark matter to the formation of galaxies. In exploring the science behind primordial black holes, we enter into a realm where the physics of the very early universe meets the most extreme objects imaginable. The idea of primordial black holes begins with the chaotic, dense conditions that existed right after the Big Bang. During the universe's infancy, it was a hot, dense soup of particles, with energy fluctuating wildly on incredibly small scales. These fluctuations are key because they could have caused regions of space to briefly become so dense that they collapsed under their own gravity, forming black holes. This process is very different from how typical black holes form today, which happens when massive stars run out of fuel and their cores collapse. Primordial black holes would have formed within the first fractions of a second after the Big Bang, when the universe was still in its early stages of expansion. Unlike black holes formed by dying stars, which need to accumulate vast amounts of matter over millions of years, primordial black holes could have popped into existence in a matter of moments, thanks to intense fluctuations in the density of the early universe. Some theories suggest that these black holes could range in size from tiny microscopic objects, no bigger than a grain of sand, to gigantic ones with the mass of thousands of suns. One key feature that distinguishes primordial black holes from their stellar mass counterparts is their potential mass range. Because primordial black holes formed in a very different way, their sizes could be much more diverse. Some might be so small that they have already evaporated due to a process called Hawking radiation, in which black holes slowly lose mass over time. Others, however, could still be out there, undetected, lurking in the dark spaces between galaxies. The formation of primordial black holes depends on several factors, most importantly the density fluctuations in the early universe. These fluctuations were caused by quantum effects that stretched out as the universe rapidly expanded during a phase called inflation. In certain regions, the density might have been high enough to overcome the natural pressure forces that were trying to smooth out the universe's distribution of matter and energy. In these regions, gravity would have taken over, causing the matter to collapse into a black hole. What makes primordial black holes particularly intriguing is that they could have formed on scales much smaller than the size of galaxies. Some of these black holes could be the size of planets or smaller, while others could rival supermassive black holes in size. Their ability to form on such small scales opens up the possibility that they could have been incredibly numerous in the early universe, potentially influencing how structures like galaxies and stars formed later on. The role of primordial black holes in the universe's evolution doesn't stop at their formation. There is a possibility that they could act as hidden gravitational anchors, affecting the distribution of matter on cosmic scales. The gravitational pull of these black holes could have helped seed the formation of galaxies, acting as points around which gas and dust could collect. This clustering of matter is crucial to galaxy formation, and primordial black holes could have played a role in shaping the large-scale structure of the universe. If primordial black holes are numerous, their gravitational influence might help explain why galaxies are grouped together in clusters, and why some regions of the universe have more matter than others. They could be responsible for the intricate web of cosmic filaments that stretch across the universe, connecting galaxies and clusters in a vast cosmic structure. In this way, primordial black holes might have shaped the universe not by emitting light or energy, but by subtly guiding the movement of matter through their gravitational influence. One of the most tantalizing aspects of primordial black holes is their potential connection to dark matter, the invisible substance that makes up roughly 85% of the universe's matter. Dark matter doesn't interact with light, making it invisible to telescopes, but we know it exists because of its gravitational effects on galaxies and galaxy clusters. Some scientists have speculated that primordial black holes could account for at least part of this dark matter. If they are numerous enough, these ancient black holes could make up a significant portion of the universe's missing mass, explaining the mysterious gravitational forces we observe in the cosmos. But detecting primordial black holes is no easy task. Unlike black holes formed by the death of stars, which often have observable effects like bright bursts of radiation when they consume matter, primordial black holes would be much more elusive. They might not have the same dramatic interactions with their environment, making them incredibly difficult to spot. Traditional methods of finding black holes, like looking for the X-rays emitted when they pull in nearby matter, might not work for primordial black holes. One possible method of detecting primordial black holes is by looking for gravitational lensing. Gravitational lensing occurs when a massive object, like a black hole, bends the light from a distant star or galaxy as it passes by. If primordial black holes exist in large numbers, we might be able to detect their presence by observing subtle changes in the light from distant objects. However, even this method has its challenges, as the lensing effects from small primordial black holes would be incredibly faint and difficult to distinguish from other cosmic phenomena. Another way to search for primordial black holes is by studying the gravitational waves they might produce. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, such as black holes merging with one another. In recent years, gravitational wave detectors like LIGO have detected the mergers of stellar mass black holes. If primordial black holes exist, they might also produce gravitational waves when they collide, though these signals would be different from those produced by larger stellar mass black holes. Scientists are actively looking for these signals, hoping to catch a glimpse of these ancient objects through the ripples they create in space-time. But perhaps the most exciting possibility is that primordial black holes could provide insight into the early universe's structure and the question of whether there is a core or central point in the cosmos. If these black holes formed shortly after the Big Bang, they could be some of the oldest objects in the universe, giving us a direct connection to the conditions of the primordial universe. Their distribution across the universe might offer clues about how the universe's large-scale structure came to be. Vacuum energy. At first glance, the term might seem contradictory. How can a vacuum, which we typically think of as empty, have any energy? Yet, in the world of quantum mechanics, even the emptiest regions of space are teeming with activity. This invisible energy, constantly fluctuating in and out of existence, plays a crucial role in the structure and evolution of the universe. From its connection to the mysterious force known as dark energy, to its implications for the future of the cosmos, vacuum energy challenges our understanding of the fundamental nature of reality. Even when space is devoid of matter, it's far from empty. The vacuum of space, according to quantum theory, is filled with quantum fluctuations. These fluctuations occur because of the Heisenberg uncertainty principle, which states that it's impossible to know both the position and momentum of a particle with perfect precision. This inherent uncertainty leads to temporary bursts of energy that manifest as particles popping in and out of existence, called virtual particles. These particles only exist for fractions of a second before they annihilate each other, but during their brief lifetimes, they create a measurable amount of energy. This energy, known as vacuum energy, exists everywhere, even in the vast emptiness of intergalactic space. While virtual particles are short-lived, their constant fluctuations contribute to the overall energy of the vacuum. The idea that empty space contains energy may seem strange, but it has been confirmed through various experiments. One of the most famous examples is the Casimir effect, where two metal plates placed extremely close to each other in a vacuum experience a tiny attractive force due to the suppression of certain quantum fluctuations between them. This effect is a direct consequence of vacuum energy at work. But vacuum energy isn't just an interesting quirk of quantum mechanics. It may also play a fundamental role in shaping the universe itself. One of the most intriguing ideas in modern cosmology is that vacuum energy might be responsible for the accelerated expansion of the universe. Over the past few decades, astronomers have discovered that the universe isn't just expanding, it's expanding faster and faster. This acceleration is thought to be driven by a mysterious force called dark energy, which makes up roughly 68% of the universe's total energy content. Dark energy acts in opposition to gravity, causing galaxies to move away from each other at an ever-increasing rate. The nature of dark energy remains one of the biggest mysteries in cosmology, but many scientists believe that vacuum energy could be the key to understanding it. If vacuum energy exists throughout space, its effects could accumulate on a cosmic scale, pushing the universe apart more and more as space itself expands. This brings us to Einstein's cosmological constant, a term he introduced in 1917 as part of his equations for general relativity. At the time, Einstein was trying to explain why the universe appeared to be static, neither expanding nor contracting. To balance the attractive force of gravity, he added the cosmological constant, a term that represented a kind of repulsive force inherent to space itself. However, after Edwin Hubble's discovery that the universe is expanding, Einstein famously called the cosmological constant his greatest mistake and abandoned the idea. Yet, decades later, with the discovery of the universe's accelerated expansion, the cosmological constant made a comeback. Today, it's considered one of the leading explanations for dark energy. In this context, the cosmological constant represents the energy of empty space, vacuum energy. Far from being a mistake, Einstein's idea might be central to understanding why the universe is expanding faster and faster. The energy of the vacuum, though tiny on small scales, could be responsible for pushing galaxies apart on cosmic scales. The implications of vacuum energy and its connection to dark energy are profound. If the accelerated expansion of the universe is indeed driven by vacuum energy, it raises questions about the fate of the universe. How the universe will evolve in the distant future depends largely on the properties of dark energy, and by extension, vacuum energy. One possible scenario is that the universe will continue to expand forever. If vacuum energy remains constant over time, the universe's expansion will never stop. galaxies will continue to drift apart until they are so far away from each other that they are effectively isolated. Over billions of years, stars will burn out, galaxies will cease forming, and the universe will grow cold and dark in a scenario known as the heat death or big freeze. In this distant future, the universe will be dominated by dark energy, with all matter spread thin across an ever-expanding void. Another possibility is that vacuum energy might change over time. If the energy of the vacuum fluctuates, it could lead to different outcomes for the universe. In one scenario, dark energy could weaken, causing the expansion to slow down and eventually stop. In this case, the universe might reverse its expansion and begin to collapse, leading to a big crunch, where all matter and energy are pulled back together into a singularity, much like the state the universe was in before the Big Bang. However, there is another, more dramatic possibility: the Big Rip. In this scenario, dark energy doesn't remain constant, but instead increases over time. If the repulsive force of dark energy continues to grow, it could eventually overcome all other forces in the universe. This would cause not just galaxies, but stars, planets, and even atoms to be torn apart. The expansion of the universe would accelerate to the point where even the fundamental particles that make up matter would be ripped apart in the final moments of cosmic existence. The dark flow. For a long time, astronomers thought they had a good handle on how the universe behaves on these grand scales. Galaxies, driven by the expansion of the universe, should be moving away from each other more or less uniformly. Unless their local gravitational environments, other galaxies or galaxy clusters nearby, alter their paths. But in 2008, something strange was observed that shook this understanding. A group of galaxy clusters located billions of light-years from Earth seemed to be moving in the same direction, all headed toward a mysterious point beyond the visible universe. This phenomenon was named the dark flow, and it raised more questions than answers. What they found was unusual. These galaxy clusters, some of the most massive structures in the universe, were moving at an unusually high speed, roughly 600 to 1,000 kilometers per second, toward a specific direction. Stranger still, this motion wasn't just random. It was consistent across a vast region of space, suggesting that something was pulling these clusters in the same direction. This movement didn't fit with our understanding of how galaxies should behave according to the standard model of cosmology. The universe is expanding, driven by dark energy, and everything within it is getting farther apart. But the galaxies and clusters within this dark flow seem to be moving toward a point far beyond the observable universe, where we can't see or measure what lies beyond. What could be pulling on these galaxies with such force? The answer, it turns out, is not simple, and it opens up the possibility that the universe is far more complex than we ever imagined. One possible explanation for the dark flow is that it's being caused by a large-scale cosmic structure that exists beyond the observable universe. The universe is filled with enormous structures, galaxy clusters, superclusters, and vast filaments of dark matter that form a web-like structure on the largest scales. These structures are shaped by gravity, and they influence the motion of galaxies and clusters. But the key limitation we face is that we can only observe part of the universe, the observable universe, which is defined by the distance light has traveled since the Big Bang. Beyond this boundary, light simply hasn't had enough time to reach us yet. However, just because we can't see beyond this cosmic horizon doesn't mean nothing is there. It's possible that the dark flow is caused by an unseen attractor, a massive region of matter or energy that lies outside our observable universe. This attractor could be pulling on the galaxies and clusters, dragging them toward it in a way that we can't fully explain based on what we currently know. While we can't observe this attractor directly, the motion of the galaxies in the dark flow gives us a clue that something is there, something massive and powerful enough to influence the movement of galaxy clusters over billions of light-years. Some scientists suggest that this unseen attractor could be a supermassive structure, perhaps another region of space that is more densely packed with galaxies, dark matter, or some other form of matter that exerts a strong gravitational pull. Others speculate that this might even be evidence of a multiverse, the idea that our universe is just one of many, and that these other universes might be interacting with ours in subtle ways. If this were true, the galaxies in the dark flow could be feeling the gravitational influence of another universe that lies beyond the cosmic horizon, pulling them toward it with a force we can't directly observe. The idea that there could be something outside our observable universe that influences what happens within it is both thrilling and unsettling. If these massive structures or forces exist, they would challenge some of the core assumptions in cosmology. Our current model of the universe, which includes the expansion driven by dark energy and the formation of galaxies influenced by dark matter, doesn't fully account for this kind of large-scale motion. The dark flow suggests that there may be a much larger and more complex structure to the universe than we previously thought, one that stretches far beyond the boundaries of what we can see. The dark flow also raises questions about the isotropy of the universe, the idea that the universe looks the same in all directions. This principle, known as the cosmological principle, is one of the foundations of modern cosmology. It suggests that, on large scales, the universe is homogeneous and isotropic, meaning that it has no preferred direction or center. But the dark flow seems to point toward a preferred direction, an area of the universe where galaxies are moving toward a specific point. If this motion is real, and not just an observational artifact, it would challenge the idea that the universe is isotropic on the largest scales. Of course, there are skeptics who argue that the dark flow might be explained by simpler means, without resorting to the idea of unseen attractors or multiverses. Some suggest that the motion observed in the dark flow could be a result of observational bias or errors in the way we interpret the data. The CMB, while incredibly useful, is difficult to measure with perfect accuracy, and some researchers believe that the apparent motion of the galaxy clusters might be a result of how we process and analyze the data. However, the fact that the dark flow has been observed in multiple studies makes it harder to dismiss as mere error. It seems that something real is happening, even if we don't yet fully understand what it is. The missing baryon problem. In the grand scale of the universe, we're made of very familiar stuff, baryons. These particles, which include protons and neutrons, form the basic building blocks of ordinary matter. Everything we can touch, see, and experience, the stars, planets, and even living beings, are composed of baryons. Yet as much as this kind of matter shapes our daily experience, it turns out we can only account for about half of the baryonic matter that theory suggests should exist. The rest, the so-called missing baryons, are nowhere to be found in the usual places we look, and their absence presents one of modern cosmology's most intriguing puzzles. The story of the missing baryon problem starts with the Big Bang. In the earliest moments after the universe's birth, baryons, protons, and neutrons were formed along with electrons and photons in a hot, dense soup of particles. Theoretical models of the early universe, based on our understanding of nuclear physics and the Big Bang, predict a specific amount of baryonic matter should have been created. As the universe expanded and cooled, this matter clumped together to form stars, galaxies, and the larger cosmic structures we observe today. But when astronomers take stock of all the matter we can see, from shining stars to vast gas clouds, we only detect about half of the expected baryons. To understand what might have happened to the rest of the baryons, it's important to first clarify what we mean by baryons and why they matter so much. Baryons are particles made up of 3 quarks. The most familiar baryons are protons and neutrons, which combine to form atomic nuclei, the building blocks of everything we consider ordinary matter. These particles account for everything we can directly observe in the universe. When we look at the sky and see stars glowing or galaxies swirling, we're seeing light emitted by baryonic matter. But astronomers have found that much of the universe's mass isn't visible in this way. This includes dark matter, which makes up about 85% of the total matter in the universe, but which doesn't interact with light or ordinary matter in the usual ways. Dark matter is an important piece of the cosmic puzzle, but it doesn't explain the missing baryons. The missing baryons are part of the ordinary matter we expect to find based on our understanding of the early universe, but they seem to be hiding in a way that makes them difficult to detect. One promising theory suggests that these missing baryons are not in stars or galaxies, but rather spread throughout the universe in the form of diffuse gas. This gas would be too faint and too cool to emit much light, making it effectively invisible to the telescopes we currently use. However, it would still exert gravitational influence, meaning it's out there, shaping the cosmos in ways we can't easily see. This diffuse gas is thought to reside in the cosmic web, the vast web-like structure that connects galaxies and galaxy clusters across the universe. The cosmic web is a network of filaments, vast strands of dark matter and gas that stretch across the universe and link galaxies and clusters together. These filaments are some of the largest structures in the cosmos, stretching for hundreds of millions of light-years. While dark matter forms the backbone of the cosmic web, it's believed that baryonic matter, particularly the missing baryons, might reside within these filaments as well, filling the spaces between galaxies in a diffuse, hard-to-detect state. If the missing baryons are hiding in these filaments, they wouldn't emit much light. Instead, they might exist as hot ionized gas that is difficult to observe. This gas could be spread thinly across vast distances, making it nearly invisible to conventional telescopes. In fact, this theory has been supported by recent observations of X-rays and quasar light passing through intergalactic space. These observations suggest that there are indeed vast amounts of ionized gas filling the spaces between galaxies, potentially accounting for the missing baryons. One way to detect this faint gas is by using quasars, extremely bright, distant objects powered by supermassive black holes. Quasars emit intense light that travels across the universe, passing through clouds of gas on its way to Earth. By studying how this light is absorbed at different wavelengths, astronomers can detect the presence of gas that might otherwise be invisible. Some of this absorption appears to come from gas in the cosmic web, hinting that the missing baryons might be hiding in these diffuse clouds of ionized gas. Another key piece of evidence comes from X-ray telescopes. The gas in the cosmic web is thought to be extremely hot, millions of degrees, causing it to emit X-rays. Observations from space telescopes like Chandra and XMM Newton have detected faint X-ray emissions coming from regions between galaxy clusters, providing further evidence that hot, ionized gas is present in these filaments. This gas, while faint, could account for a significant portion of the missing baryons, helping to fill in the gaps in our cosmic inventory. The existence of these missing baryons in the cosmic web also helps to explain the large-scale structure of the universe. As the universe evolved, gravity pulled matter together into dense regions, forming galaxies and clusters of galaxies. But much of the matter in the universe didn't form into stars or galaxies. Instead, it remained in a more diffuse state, spread out along the cosmic web's filaments. These filaments act as highways for matter to travel along, connecting galaxy clusters and helping to shape the universe's structure. This hidden structure, composed of dark matter and diffuse gas, plays a crucial role in the evolution of galaxies. As gas flows along these filaments, it can fall into galaxies and feed star formation. In this way, the cosmic web not only connects galaxies, but also helps to fuel their growth. The missing baryons, if they are indeed hiding in these filaments, are an essential part of this process, acting as the invisible scaffolding that holds the universe together. The cosmic web's filaments also offer a clue as to how galaxies form and cluster together. When we look at the large-scale structure of the universe, we see that galaxies are not evenly distributed. Instead, they form clusters and superclusters with vast voids between them. These structures are shaped by the cosmic web, which acts as a kind of framework for the universe's growth. The missing baryons, if spread out in these filaments, would help to explain why galaxies and clusters form in these specific patterns, rather than being randomly scattered across space. Despite these advances, the search for the missing baryons is far from over. While there is growing evidence that they exist in the cosmic web's filaments, there are still many uncertainties about how much of this matter we've accounted for. Some of the missing baryons might still be hiding in other forms, such as cooler, less ionized gas, or even in the outer regions of galaxies that are difficult to observe. The Eridanus supervoid. In the vast, intricate structure of the universe, most regions of space are filled with galaxies, stars, and other cosmic material. However, not all areas of the cosmos are equally populated. Some regions, known as voids, are strikingly empty, containing far fewer galaxies than expected. One of the most fascinating of these is the Eridanus supervoid, an enormous region of space that appears to be unusually empty and cold. This supervoid is tied to one of the greatest mysteries in modern cosmology, a cold spot in the cosmic microwave background. The Eridanus supervoid has become the subject of intense interest because of its possible connection to this cold spot. The CMB is remarkably uniform, but it has small fluctuations in temperature, tiny differences that reflect the conditions of the early universe. Among these fluctuations, one area stands out as being significantly colder than its surroundings. This CMB cold spot, located in the direction of the constellation Eridanus, is much colder than the standard models of the universe would predict. Scientists have been trying to understand what could be causing this anomaly, and the discovery of the Eridanus supervoid in the same direction provides a potential explanation. At first glance, the existence of a cold spot in the CMB might not seem that surprising. After all, the CMB itself is not perfectly uniform, with small variations in temperature that are attributed to differences in density in the early universe. These variations are crucial for the formation of galaxies and other cosmic structures, providing the seeds around which matter coalesced. But the Eridanus cold spot is different. It's much larger and colder than other fluctuations, raising questions about what could have caused such an extreme anomaly. One leading explanation is that the Eridanus supervoid, a massive region of space with far fewer galaxies and matter than expected, might be responsible for this cold spot. Supervoids are not uncommon in the universe. Voids of various sizes are scattered throughout the cosmic web, the large-scale structure of the universe. These voids are regions where the density of matter is lower than average, and they can span hundreds of millions of light-years. But the Eridanus supervoid stands out because of its size and the possibility that it is linked to the CMB cold spot. The relationship between the supervoid and the cold spot could be explained by a phenomenon known as the Sachs-Wolf effect, which involves how light behaves as it passes through regions of varying gravitational strength in the universe. When photons from the CMB pass through a supervoid, they encounter less gravitational pull compared to regions with more matter. As they enter the void, they are blue-shifted, gaining energy as they fall into the gravitational potential of the void. However, as the photons leave the void, they lose energy, becoming red-shifted. This loss of energy can create a cooling effect, where the CMB photons that pass through the void end up with slightly less energy, making the region appear colder when viewed from Earth. In the case of the Eridanus supervoid, the size of the void could be amplifying this Sachs-Wolf effect. As CMB photons travel through this vast, underdense region of space, they lose energy, resulting in the cold spot we see in the CMB. While this explanation fits well with what we observe, it's not yet definitive. The Sachs-Wolf effect alone might not fully account for the extreme coldness of this region, leading some scientists to speculate that other, more complex factors might be at play. One of the big questions surrounding the Eridanus supervoid is whether it's a unique anomaly or part of a larger pattern of cosmic structure. Voids like this are an integral part of the universe's large-scale architecture. The cosmic web, which consists of galaxies, galaxy clusters, and dark matter, is interconnected by vast filaments of matter. In between these filaments are voids, regions where matter is much more sparse. These voids, including the Eridanus supervoid, help define the shape and structure of the universe. But most voids don't produce such a pronounced effect on the CMB. So why does this one? One possibility is that the Eridanus supervoid is part of a larger, more complex structure that we don't yet fully understand. Some researchers have suggested that it might be connected to other nearby voids, forming a kind of superstructure in the cosmic web. If this were the case, it could provide a clue about how the universe's large-scale structure evolved, offering insights into the nature of dark matter and the distribution of galaxies. This idea is still speculative, but it raises the intriguing possibility that the Eridanus supervoid could be a piece of a much larger puzzle, one that could reshape our understanding of how matter is distributed throughout the universe. There's also the possibility that the Eridanus supervoid might not be the only factor responsible for the CMB cold spot. Some theories suggest that the cold spot could be the result of more exotic phenomena, such as the influence of dark energy or even interactions with other universes. In some versions of the multiverse theory, our universe is just one of many, and the cold spot could be a sign of a collision or interaction between our universe and another. While this idea is highly speculative, it highlights how little we know about the fundamental nature of the cosmos and the forces that shape it. The discovery of the Eridanus supervoid has prompted a re-examination of how voids and other large-scale cosmic structures influence the universe. Voids are fascinating because they provide a unique environment in which to study the effects of gravity and dark matter. In dense regions like galaxy clusters, the gravitational pull of matter is strong, and galaxies move according to well-understood gravitational dynamics. But in voids, where there is much less matter, the rules of cosmic evolution can play out differently. One of the key challenges in studying voids like the Eridanus supervoid is that they are difficult to detect. Unlike galaxies or clusters which emit light and can be easily seen with telescopes, voids are defined by what's missing. To find them, astronomers must carefully map the distribution of galaxies and look for regions where the density of galaxies is significantly lower than expected. The Eridanus supervoid, for example, was detected by mapping the distribution of galaxies in the region and noticing a large area where very few galaxies exist. Despite these challenges, voids provide a wealth of information about the universe's structure and evolution. By studying how galaxies and matter are distributed in and around voids, scientists can learn more about the processes that drive the formation of cosmic structures. Voids also offer a unique way to test theories of dark energy, the mysterious force driving the accelerated expansion of the universe. Some models of dark energy predict that it should have different effects in regions of varying density, making voids an important laboratory for testing these ideas. Creating matter at the universe's core. According to what we know of particle physics, the early universe, born from the intense heat of the Big Bang, should have created equal amounts of matter and antimatter. Each particle of matter, proton, neutron, and electron, should have a counterpart in antimatter. Antiprotons, antineutrons, and positrons. When these two meet, they annihilate one another, converting into pure energy. But when we observe the universe today, what we see are stars, galaxies, planets, and people, almost entirely made of matter with no significant amounts of antimatter in sight. The process that resulted in the dominance of matter over antimatter is called baryogenesis, and understanding it remains one of the greatest challenges in both cosmology and particle physics. The core of this mystery lies in the imbalance between baryons, particles like protons and neutrons, and their antimatter equivalents. The universe should have been a perfect balance between the two, leaving us with a universe full of radiation, but devoid of the matter that makes up the stars and galaxies. Instead, a tiny fraction of matter survived, leading to the formation of the universe as we know it. This small excess of matter over antimatter, on the order of 1 extra baryon for every billion baryon-antibaryon pairs, was enough to create everything we see. But why did this imbalance occur? What process led to the creation of more matter than antimatter in the early universe? To explain how baryogenesis might have happened, Russian physicist Andrei Sakharov proposed a set of conditions that must be met. First, the laws of physics had to allow for violations in what's known as baryon number conservation. Normally, particle interactions conserve the number of baryons, meaning the total number of protons and neutrons remains constant. However, for baryogenesis to occur, there must be processes that allow for the creation or destruction of baryons. This violation would permit an imbalance between matter and antimatter. Additionally, Sakharov identified the need for violations of symmetries, specifically charge parity symmetry or CP symmetry. CP symmetry means that the universe should treat particles and antiparticles identically. If this symmetry were perfectly preserved, there would be no way to produce more matter than antimatter. The breaking of this symmetry allowed the universe to favor matter over antimatter. Finally, the universe had to be in a state that was not in thermal equilibrium. In thermal equilibrium, all processes would occur in such a way that the production and destruction of baryons and antibaryons would balance out, preventing any asymmetry from developing. However, in the chaotic, rapidly expanding early universe, there were regions out of equilibrium, where these conditions could have led to the imbalance we observe today. These three conditions, known as the Sakharov conditions, provide a theoretical framework for baryogenesis, but the exact mechanism behind this imbalance remains an open question. One of the most prominent theories to explain baryogenesis is related to the physics of the electro-weak phase transition. This transition occurred when the universe was only fractions of a second old, as the temperature dropped to a critical level, and the electromagnetic and weak nuclear forces separated into distinct forces. During this phase transition, certain processes could have violated both baryon number conservation and CP symmetry, setting the stage for the creation of more matter than antimatter. While the standard model of particle physics includes some CP violation, the amount predicted is far too small to explain the observed imbalance. This has led scientists to explore theories beyond the standard model, such as supersymmetry, which predicts additional sources of CP violation that could account for the excess of matter. Another intriguing idea is leptogenesis, a process that connects the matter-antimatter asymmetry to the behavior of leptons, a family of particles that includes electrons and neutrinos. In leptogenesis, an asymmetry between leptons and antileptons is generated first, and this asymmetry is then transferred to baryons through interactions that violate both baryon and lepton number conservation. This theory is appealing because it connects the mystery of baryogenesis to the poorly understood properties of neutrinos. Neutrinos are incredibly light particles that barely interact with matter, making them difficult to study. But they could hold the key to understanding why the universe is filled with matter rather than antimatter. Theories like electroweak baryogenesis and leptogenesis are grounded in the extreme conditions of the early universe, when temperatures and energies were vastly higher than anything we can observe today. During this time, the universe was a chaotic sea of elementary particles constantly interacting and transforming. As the universe expanded and cooled, these particles settled into the forms we see today, but the processes that led to baryogenesis would have occurred during this brief window of incredibly high energy. Some researchers have speculated that inflation, a period of rapid expansion in the early universe, could have played a role in creating the right conditions for baryogenesis. Inflation not only smoothed out the universe on large scales, but also drove regions out of thermal equilibrium, potentially allowing the necessary asymmetry to form. While these theories provide promising explanations, the question remains whether baryogenesis occurred uniformly throughout the universe or whether it was concentrated in specific regions. If the conditions for baryogenesis were met uniformly, then the matter-antimatter asymmetry would have arisen in the same way across the entire cosmos. However, if baryogenesis was more localized, it raises the possibility that certain regions of the universe were more prone to generating excess matter than others, potentially pointing to some sort of central event or process. Some scientists have speculated that baryogenesis might have been influenced by topological defects, structures like cosmic strings or domain walls that could have formed during phase transitions in the early universe. These defects might have concentrated the process of baryogenesis in certain areas, creating localized regions of matter dominance. While there is little direct evidence for such structures, they remain an intriguing possibility that could explain why baryogenesis occurred in the way it did. Even with these tantalizing possibilities, most models suggest that baryogenesis was a universal process occurring throughout the early universe as a result of the fundamental forces and interactions at play. This would be consistent with the cosmological principle, which holds that the universe is homogeneous and isotropic on large scales, meaning that the same physical processes occurred everywhere. Nevertheless, the precise nature of baryogenesis and how it was distributed across the universe remains an active area of research. To uncover the secrets of baryogenesis, physicists are looking both to the cosmos and to the subatomic world. High-energy particle accelerators like the Large Hadron Collider (LHC) offer a way to probe the conditions of the early universe by recreating the extreme temperatures and energies that existed just after the Big Bang. These experiments can reveal new particles and interactions that might help explain how baryogenesis occurred. In particular, scientists are searching for signs of new physics beyond the standard model that could account for the additional CP violation needed to generate the matter-antimatter asymmetry. At the same time, astronomers are studying the large-scale structure of the universe, the distribution of galaxies, and the behavior of fundamental particles like neutrinos. By understanding how matter is distributed across the cosmos, researchers hope to uncover clues about the processes that shape the universe in its earliest moments. Neutrinos, in particular, hold promise for shedding light on baryogenesis, as their properties are still not fully understood, and they could play a crucial role in the mechanisms that created the imbalance between matter and antimatter. Finding the universe's center of mass. A barycenter is a familiar concept in many aspects of physics and astronomy. It is the point around which all the mass in a system is balanced, often thought of as the center of mass. In smaller systems, such as the Earth and the Moon, the barycenter is the point where the gravitational forces between the two bodies balance out, located not in the center of one of the objects but rather at a point in space, determined by their relative masses. This concept can be extended to larger scales, such as the solar system, where the Sun does not sit perfectly still at the center, but moves slightly in response to the gravitational pull of the planets. At even larger scales, like that of galaxies and clusters, the idea of a barycenter continues to apply. However, when we scale up this concept to the entire universe, things become far more complex and intriguing. Is there a single point around which all the mass in the universe balances? And if so, what would that tell us about the structure and movement of the cosmos? The notion of a cosmic barycenter, essentially the center of mass of the entire universe, is both captivating and challenging. In any system, a barycenter is defined as the point where the gravitational forces of all masses balance out. For the universe, this would theoretically be the point where all the matter, from galaxies to dark matter and everything in between, finds equilibrium. But the universe is not a simple, localized system like a planet or a star. It is a vast, expanding collection of galaxies, superclusters, and other cosmic structures, all moving in response to a complex interplay of gravitational forces. This makes the idea of identifying a single barycenter for the universe far more complicated than it is for more localized systems. On smaller scales, a barycenter is relatively easy to define because we can observe how masses interact with each other. In a two-body system, such as a planet orbiting a star, the barycenter is straightforward to calculate because there are only two objects to consider, and their positions and masses are well understood. When it comes to galaxies or clusters of galaxies, the barycenter becomes more difficult to pinpoint because we are dealing with many objects, each with its own mass and velocity, interacting through the gravitational force. However, in these cases, we can still define a barycenter by summing up the contributions of all the masses in the system and determining the point where they balance. But when we extend this concept to the universe as a whole, several complications arise. The universe is constantly expanding, driven by dark energy, and filled with not just ordinary matter but also dark matter and other forms of energy that we still do not fully understand. Additionally, the universe does not appear to have a single fixed point in space where all the matter is concentrated. Instead, matter is spread out in a web-like structure, with galaxies and clusters of galaxies connected by filaments of dark matter. This structure, known as the cosmic web, presents a challenge to the idea of a single cosmic barycenter because it suggests that the distribution of mass in the universe is not uniform or concentrated in any one place. One way to think about the barycenter of the universe is to consider how galaxies and clusters interact gravitationally on the largest scales. Galaxies are not evenly distributed across space but are instead clumped together in clusters and superclusters, which are themselves connected by vast filaments of dark matter. These structures form the cosmic web, and their gravitational interactions influence how matter is distributed across the universe. The idea of a barycenter at this scale would involve finding the point where the gravitational forces of all these massive structures balance out. However, one of the main challenges to defining a universal barycenter is that the universe is expanding. This expansion is driven by dark energy, a mysterious force that causes the space between galaxies to stretch. Because of this expansion, galaxies are not only moving due to gravitational interactions, but also because of the expansion of space itself. This means that any attempt to define a cosmic barycenter would have to take into account both the gravitational forces between galaxies and the effects of cosmic expansion. The question becomes, can a barycenter exist in a universe that is constantly expanding and where distances between objects are increasing? In theory, a barycenter could still exist in an expanding universe, but it would not be static or fixed in any one place. Instead, it would be a dynamic point that shifts over time as the universe evolves and as galaxies and other cosmic structures move. The expansion of the universe introduces a form of cosmic drift, making the idea of a permanent or absolute barycenter much more difficult to pin down. Nevertheless, on shorter timescales, it is possible to imagine a point where the mass of the universe finds a temporary balance, even as this point changes with the ongoing expansion. The concept of a cosmic barycenter becomes even more intriguing when we consider the role of dark matter. Dark matter, which makes up about 85% of the matter in the universe, does not interact with light or other forms of electromagnetic radiation, making it invisible to telescopes. However, its presence is inferred through its gravitational effects, and it plays a crucial role in shaping the cosmic web and the movement of galaxies. The mass of dark matter would have to be included in any calculation of the universe's barycenter, but because dark matter is spread out in diffuse halos around galaxies and clusters, this complicates the task even further. The barycenter would need to account for not only the visible matter in galaxies, but also the unseen mass of dark matter that dominates the universe's total mass. If we could determine the universe's barycenter, or at least an approximation of it, it could provide insights into the large-scale structure of the universe and how mass is distributed across space. By understanding the balance point of the universe's mass, we might be able to better comprehend how galaxies and superclusters are arranged and how they move relative to each other. This, in turn, could give us a deeper understanding of the forces shaping the cosmic web and the role that dark matter plays in holding the universe together. One of the most fascinating implications of finding a cosmic barycenter is the possibility that it could point to a central organizing structure or process in the universe. If the mass of the universe can be balanced at a single point, does that suggest that there is a central gravitational core that influences the movement and distribution of matter on a large scale? In most current models of cosmology, the universe does not have a single center. The cosmological principle holds that the universe is homogeneous and isotropic on large scales, meaning that it looks the same in all directions and has no preferred location. This suggests that there is no central point from which the universe is expanding, and no single location can be identified as the center of the universe. However, some scientists have speculated that the distribution of matter and energy in the universe might not be entirely uniform and that there could be anisotropies, regions where the density of matter is higher than in other parts of the universe. If these anisotropies exist, they could act as gravitational attractors, pulling matter toward them and creating a form of cosmic equilibrium. This could, in theory, lead to a shifting barycenter that moves over time as galaxies and clusters migrate toward these attractors. Another possibility is that the universe's barycenter could be influenced by gravitational interactions on the largest scales. Just as individual galaxies move in response to the gravitational pull of nearby clusters, entire superclusters could be moving toward massive attractors located beyond the observable universe. These attractors, if they exist, could act as the focal points of the universe's gravitational field, creating a dynamic and shifting barycenter. This idea is supported by observations of large-scale cosmic flows, such as the dark flow, where clusters of galaxies appear to be moving toward a point beyond the visible universe. These flows could be the result of gravitational forces exerted by unseen structures or regions, potentially altering the universe's barycenter over time. Hawking radiation, black hole. Evaporation in the universe's core. Hawking radiation is one of the most fascinating and revolutionary concepts in theoretical physics, particularly because it challenges the traditional understanding of black holes as entities from which nothing, not even light, can escape. Introduced by the renowned physicist Stephen Hawking in 1974, this theory suggests that black holes are not as isolated from the universe as previously thought. In fact, they emit a faint form of radiation due to quantum effects near their event horizons, the invisible boundary that marks the point of no return around a black hole. This radiation causes black holes to lose mass over time, leading to the possibility that they could eventually evaporate entirely. Hawking's theory not only reshaped our understanding of black holes, but also opened up new questions about the universe's deepest mysteries. The idea behind Hawking radiation stems from the peculiarities of quantum mechanics, which governs the behavior of particles on the smallest scales. According to quantum theory, even in the vacuum of space, particle-antiparticle pairs are constantly forming and annihilating. These virtual particles exist for only a brief moment before they collide and vanish. But near the event horizon of a black hole, this process plays out differently. When a particle-antiparticle pair forms near the event horizon, the black hole's intense gravitational pull can sometimes separate the pair. One of the particles falls into the black hole, while the other escapes into space. The particle that escapes appears as radiation, and the black hole loses a tiny bit of mass in the process, a phenomenon now known as Hawking radiation. This process may seem insignificant at first glance. After all, black holes are incredibly massive objects, and the amount of mass lost through Hawking radiation is minuscule. But over long periods of time, particularly for smaller black holes, this radiation could lead to the gradual evaporation of the black hole. In the case of stellar mass black holes, which are formed by the collapse of massive stars, the rate of Hawking radiation is exceedingly slow. It would take far longer than the current age of the universe for these black holes to evaporate. However, for primordial black holes, which may have formed in the early universe, the situation could be quite different. Primordial black holes are hypothetical objects that would have formed during the chaotic moments just after the Big Bang, when regions of space experienced extreme fluctuations in density. These black holes could be much smaller than stellar mass black holes, with some potentially having masses comparable to that of a large asteroid or even less. For these smaller black holes, Hawking radiation would be far more significant. Because smaller black holes emit radiation more intensely than larger ones, primordial black holes would lose mass more quickly and could, in theory, evaporate entirely over the course of billions of years. The possibility of evaporating primordial black holes is particularly exciting because it could offer insights into the nature of the early universe. If primordial black holes exist, they could serve as relics of the conditions present just moments after the Big Bang. Studying them could reveal important clues about the formation of large-scale cosmic structures, the distribution of dark matter, and even the behavior of the fundamental forces in the universe's infancy. As these black holes evaporate, the radiation they emit could provide a glimpse into processes that occurred at the universe's very beginning, processes that we cannot otherwise observe. Primordial black holes could also serve as natural laboratories for testing the limits of quantum mechanics and general relativity, the two pillars of modern physics. Hawking radiation exists at the intersection of these two fields, combining the quantum effects that govern particles with the intense gravitational fields described by Einstein's theory of general relativity. This makes evaporating black holes a prime candidate for exploring the so-called theory of everything, the elusive unified theory that would explain both the quantum world and the large-scale structure of the universe. If primordial black holes are evaporating through Hawking radiation, studying the characteristics of this radiation could help physicists understand how these two fundamental theories interact at extreme scales. One particularly intriguing question is whether Hawking radiation could reveal anything about the cosmic core, the idea of a central region or structure in the universe that influences its large-scale behavior. While the universe is generally thought to be isotropic and homogeneous, meaning it looks the same in all directions on large scales, there could be regions where matter is more densely concentrated, such as near supermassive black holes or clusters of galaxies. If black holes, particularly primordial black holes, are evaporating through Hawking radiation in these regions, their radiation could provide clues about the nature of these cosmic structures. For example, if Hawking radiation were detected near the center of a massive galaxy cluster, or even in the vicinity of supermassive black holes, it could help scientists understand the gravitational dynamics at play in these regions. Supermassive black holes, like the one at the center of the Milky Way, Sagittarius A, have masses millions or even billions of times that of the Sun. These objects dominate their surrounding environments, pulling in gas, dust, and stars with their immense gravitational fields. While the Hawking radiation from a supermassive black hole would be almost imperceptible, the presence of evaporating primordial black holes nearby could help map the structure and distribution of matter in these regions. Moreover, Hawking radiation might offer a way to probe the dark matter halos that envelop galaxies and clusters. Dark matter, which makes up about 85% of the matter in the universe, is invisible to telescopes because it does not interact with light in the same way that ordinary matter does. However, its presence is inferred through its gravitational effects, and it is thought to play a key role in the formation and stability of large cosmic structures. If primordial black holes exist within dark matter halos and are evaporating through Hawking radiation, their radiation could provide indirect evidence of the nature and distribution of dark matter in these regions. Detecting such radiation would be a monumental step forward in solving the dark matter puzzle. Exotic particles hidden in the universe's core. In every magnet we encounter, whether it be a refrigerator magnet or the magnetic field of the Earth, there are always two poles, a north and a south. Cut a magnet in half, and each piece will still have both a north and a south pole. However, magnetic monopoles would behave differently. Instead of having both poles, they would carry a single magnetic charge, either north or south. This asymmetry would make them unlike any other particle known to exist. The idea of magnetic monopoles dates back to the early 20th century and became more formalized when physicist Paul Dirac, in 1931, suggested that the existence of monopoles could explain why electric charge is quantized. In simple terms, this means that electric charge only appears in discrete units, such as the charge of an electron or a proton. Dirac showed that the existence of even a single magnetic monopole in the universe could explain why electric charge always comes in these specific units. Despite this elegant theoretical foundation, no magnetic monopoles have ever been observed, leaving their existence as one of the great open questions in theoretical physics. The theoretical importance of magnetic monopoles goes beyond just explaining the quantization of charge. Monopoles are also predicted by grand unified theories, GUTs, which attempt to unify the three fundamental forces of nature, electromagnetism, the weak nuclear force, and the strong nuclear force, into a single theoretical framework. According to these theories, magnetic monopoles would have formed in the very early moments after the Big Bang, during a phase transition when the forces of nature separated from one another. If these monopoles do exist, they would represent a profound link to the earliest moments of the universe and could provide crucial insights into the conditions that shaped the cosmos in its infancy. In grand unified theories, magnetic monopoles are expected to be incredibly massive, far more so than ordinary particles like electrons or protons. This makes them difficult to produce in particle accelerators, even in the most powerful ones like the Large Hadron Collider, LHC. Furthermore, monopoles would interact weakly with ordinary matter, meaning they could pass through vast regions of space without leaving a detectable trace. This combination of high mass and weak interaction makes magnetic monopoles extremely challenging to detect, even though they could theoretically exist in significant numbers. The search for magnetic monopoles has been ongoing for decades, with scientists devising a variety of clever experiments to try to detect these elusive particles. One of the earliest efforts took place in the 1970s, when researchers set up detectors to search for monopoles passing through the Earth. These detectors were designed to look for the distinctive magnetic signature that a monopole would produce as it moved through matter. While there have been a few claims of monopole detections over the years, none have been conclusively confirmed, and the search continues. In addition to ground-based detectors, scientists have also looked to cosmic rays and astronomical observations as potential sources of monopoles. Cosmic rays are high-energy particles that travel through space, originating from sources such as supernovae and active galactic nuclei. If magnetic monopoles were produced in the early universe, some of them could still be drifting through space, carried along by the same processes that accelerate cosmic rays. By analyzing cosmic ray data, scientists hope to detect the telltale signs of a monopole interacting with other particles. However, no monopole signatures have yet been found in cosmic ray data. The discovery of magnetic monopoles would represent a profound shift in our understanding of the universe's structure and the fundamental forces that govern it. Monopoles would be a new class of elementary particles, unlike anything currently included in the standard model of particle physics, which describes the behavior of all known particles and forces except gravity. If monopoles exist, their discovery would force physicists to revise the standard model and could provide a crucial piece of the puzzle needed to unify the forces of nature under a single theoretical framework. One of the most intriguing questions about magnetic monopoles is whether they could offer clues to a central point or structure in the universe. While the universe is generally thought to be homogeneous and isotropic on large scales, meaning it looks the same in all directions, there are certain regions of space, such as the centers of galaxies and galaxy clusters, where matter is more densely concentrated. If magnetic monopoles formed in the early universe, they might be more concentrated in these massive regions, where gravitational forces could draw them together over billions of years. In particular, monopoles could be concentrated near supermassive black holes or the centers of galaxy clusters, where the gravitational pull is strongest. These massive regions of space act as cosmic sinks, pulling in not just ordinary matter but also dark matter and other exotic particles. If magnetic monopoles exist, they could be drawn into these regions over time, forming a dense population of monopoles near the cores of galaxies or clusters. Detecting monopoles in such regions could provide valuable insights into the distribution of mass and energy in the universe, as well as the forces that govern cosmic structures on the largest scales. Some physicists have speculated that magnetic monopoles could also be linked to topological defects, hypothetical structures that may have formed in the early universe during phase transitions. These defects, such as cosmic strings or domain walls, could have concentrated monopoles in certain regions of space, leading to a non-uniform distribution of monopoles across the universe. If such structures exist, they could provide a natural explanation for the locations of magnetic monopoles, and their discovery would offer new insights into the nature of space-time itself. The possibility that magnetic monopoles could be concentrated in massive regions of the universe raises fascinating questions about their role in the evolution of cosmic structures. If monopoles are drawn to the centers of galaxies or galaxy clusters, they could influence the dynamics of these systems in subtle but important ways. For example, monopoles could interact with magnetic fields in these regions, altering the behavior of charged particles and potentially affecting processes such as star formation or the movement of interstellar gas. While the precise role that monopoles might play in these systems is still speculative, their presence could open up new avenues of research in astrophysics and cosmology. Beyond their potential concentration in massive cosmic regions, the discovery of magnetic monopoles could also offer clues to early cosmic events. Because monopoles are predicted to have formed during a phase transition in the early universe, their properties could provide information about the conditions that existed just after the Big Bang. Studying monopoles could help physicists understand the nature of the forces that governed the early universe. and how those forces evolved into the ones we observe today. In particular, if magnetic monopoles were discovered and their distribution mapped across the universe, it could offer insights into the geometry and structure of space-time itself. Monopoles are tied to fundamental symmetries in nature, and their presence could reveal deep connections between the forces that shaped the universe. Understanding these symmetries could bring us closer to a unified theory that explains both the large-scale structure of the universe and the behavior of elementary particles. Neutrino astronomy. Ghost particles as clues to the universe's heart. Unlike photons, which are easily absorbed or scattered by particles, neutrinos can pass through entire stars, planets, and even galaxies virtually unimpeded. This remarkable property makes them ideal for studying the most extreme and inaccessible regions of space, from the fiery cores of stars to the hidden depths of the universe. In recent decades, the field of neutrino astronomy has emerged as a powerful tool for probing the cosmos, offering new insights into the processes that shape the universe and its evolution. Neutrinos are elementary particles that belong to the family of leptons, alongside electrons and muons. One of their most defining characteristics is their incredibly small mass. So small, in fact, that for many years scientists thought neutrinos might be massless. However, experiments have since shown that neutrinos do have a tiny mass, although it is still much smaller than that of other subatomic particles. Neutrinos come in 3 different types or flavors: electron neutrinos, muon neutrinos, and tau neutrinos, each corresponding to their charged lepton counterparts. These particles are produced in vast numbers by nuclear reactions, such as those that occur inside stars, in supernovae, and during radioactive decay processes on Earth. Despite their abundance, trillions of neutrinos pass through each of us every second. They are incredibly difficult to detect. This is because neutrinos interact with matter only through the weak nuclear force, one of the 4 fundamental forces of nature. This weak interaction means that neutrinos can pass through dense objects like stars or planets without being absorbed or scattered. A neutrino could pass through a wall of lead several light-years thick without hitting anything. This makes neutrinos both fascinating and frustrating for scientists, as they are abundant and travel great distances, yet detecting them requires extremely sensitive and sophisticated instruments. The ability of neutrinos to pass through dense matter makes them invaluable tools for studying the cores of stars and other dense cosmic structures. Unlike photons, which are emitted from the surface of stars and can be absorbed or scattered along the way, neutrinos are produced in the very heart of stars, where nuclear fusion occurs. These particles carry information about the nuclear reactions taking place in the star's core, offering a direct window into the processes that power the universe's brightest and most energetic objects. One of the most well-known sources of neutrinos is the Sun. The Sun produces vast quantities of neutrinos through the process of nuclear fusion, where hydrogen atoms are fused together to form helium, releasing energy in the form of light and neutrinos. The neutrinos produced in the Sun's core travel outward and escape into space without being absorbed, providing scientists with a direct line of sight into the solar interior. By studying these solar neutrinos, scientists have been able to test models of stellar fusion and improve our understanding of how stars like the Sun generate energy over billions of years. Neutrino detectors, such as the Super Kamiokande experiment in Japan or the IceCube Neutrino Observatory located beneath the Antarctic ice, are designed to catch these elusive particles. These detectors work by observing the rare interactions between neutrinos and the atoms in large volumes of water or ice. When a neutrino collides with an atom, it produces a faint flash of light called Cherenkov radiation, which can be detected by sensitive instruments. While these interactions are rare, the sheer number of neutrinos passing through the detectors allows scientists to collect enough data to study the properties of these ghostly particles. In addition to studying solar neutrinos, neutrino astronomy has allowed scientists to detect neutrinos from supernovae, the explosive deaths of massive stars. When a star goes supernova, it releases a tremendous amount of energy in the form of light, heat, and neutrinos. These neutrinos escape the collapsing star long before any visible light can emerge, providing an early warning signal that a supernova has occurred. The detection of neutrinos from supernova 1987A, located in the Large Magellanic Cloud, was a groundbreaking moment in neutrino astronomy. It confirmed theoretical predictions about how stars explode and showed that neutrinos play a critical role in the collapse of a dying star's core. The unique properties of neutrinos make them invaluable for probing the densest and most extreme regions of space, including the hearts of galaxies and potentially the core of the universe itself. Since neutrinos can travel through vast amounts of matter without being absorbed, they can pass through cosmic structures that would otherwise block or obscure light. This makes neutrinos excellent messengers from regions of space that are difficult or impossible to observe using traditional telescopes. For example, neutrinos produced by black holes and active galactic nuclei, AGN, are of particular interest to scientists. AGNs are supermassive black holes at the centers of galaxies that are actively consuming large amounts of matter, generating enormous amounts of energy in the process. These regions are so dense and energetic that they produce high-energy neutrinos, which can escape and travel across the universe. By studying these neutrinos, scientists hope to gain insights into the behavior of supermassive black holes and the processes that power AGNs, helping to unravel the mysteries of how galaxies form and evolve. Neutrino astronomy also offers the potential to probe the early universe, shedding light on its structure and evolution. Neutrinos were produced in vast quantities during the Big Bang, and these primordial neutrinos, known as the cosmic neutrino background, still permeate the universe today. While these neutrinos have much lower energies than the ones produced in stars or supernovae, detecting them could provide a direct window into the conditions that existed just moments after the universe began. Studying these relic neutrinos from the Big Bang could help scientists answer fundamental questions about the universe's expansion and the distribution of matter. For example, neutrinos could offer clues about the distribution of dark matter, the invisible substance that makes up about 85% of the universe's mass. Since neutrinos are weakly interacting particles like dark matter, they could be used to trace the gravitational effects of dark matter and map its distribution across the cosmos. Furthermore, neutrinos may hold the key to understanding whether the universe has a central core or some form of central structure. While the standard cosmological model suggests that the universe is homogeneous and isotropic on large scales, meaning it looks the same in every direction, there are still open questions about the large-scale structure of the universe. Neutrinos, due to their weak interactions and ability to travel through dense matter, could provide unique information about any hidden regions of the universe that are inaccessible to photons or other particles. Cyclic universe theory. The cyclic universe theory offers an alternative perspective to the widely accepted view of a one-time Big Bang, followed by the continuous expansion of the universe. According to this theory, the universe does not have a single beginning or an inevitable end. Instead, it experiences an ongoing series of cycles of expansion and contraction, punctuated by moments of rebirth. This idea suggests that the universe has been expanding and collapsing in a rhythmic sequence of big bangs and big crunches for eternity. Each cycle brings about the destruction of the old universe and the creation of a new one, suggesting that the cosmos may have no true beginning or end, only an endless series of renewals. At the heart of the cyclic universe theory is the idea of the Big Bang Big Crunch cycle. The theory posits that the universe, after a period of expansion following the Big Bang, will eventually stop expanding and begin to contract due to the gravitational pull of all the matter in the universe. This contraction leads to what is known as the Big Crunch, a hypothetical scenario in which the entire universe collapses back in on itself. All the galaxies, stars, and cosmic structures would be drawn back together, ultimately compressing into a singularity, a point of infinite density and temperature, much like the initial conditions that led to the Big Bang. This cyclic nature of the universe proposes that after the Big Crunch, the universe could bounce back into another expansion, igniting a new cycle in a process that might repeat indefinitely. In this view, the universe would have gone through countless such cycles of expansion and contraction, with each Big Bang giving rise to a new universe and each Big Crunch leading to its temporary destruction. This concept fundamentally challenges the idea that the universe began with a single Big Bang and is destined to expand forever into a cold, lifeless void, as predicted by the standard model of cosmology. The central point in the cyclic universe theory is key to understanding how these cycles of creation and destruction might occur. As the universe contracts during the Big Crunch, all matter and energy would theoretically collapse toward a single point or a region of extreme density. This idea raises the question of whether the universe has a sort of cosmic core, a central region that acts as the gravitational and energetic focus of these cycles. In many models of the cyclic universe, this cosmic core represents the point at which the universe reaches its maximum density before rebounding into a new cycle of expansion. This cosmic core would be the point where all matter, energy, and space-time converge during the Big Crunch. The intense gravitational forces in this region would be so powerful that even light could not escape, compressing everything into a singularity, a state of infinite density. It is from this singularity that the next phase of the universe would emerge. Some theorists suggest that this core could be a remnant of previous cycles, containing the seeds of future universes. In this sense, the universe could be viewed as constantly collapsing and expanding around a central cosmic point, where each new cycle begins from the ashes of the previous one. One of the most interesting aspects of the cyclic universe theory is how it reframes the concept of creation and destruction. Rather than viewing the universe as a single, linear progression from the Big Bang to an eventual heat death, as predicted by the current standard model, the cyclic universe theory suggests that the universe is continually reborn. After each Big Crunch, the universe would be reborn in a new Big Bang, leading to the creation of new galaxies, stars, and cosmic structures. In this scenario, the cosmos is constantly renewing itself, with each cycle building on the conditions left behind by the previous one. The idea of constant creation and rebirth raises profound questions about the nature of time and existence. In the cyclic model, time would not have a clear beginning or end. Instead, it would loop infinitely, with each cycle representing a new iteration of the universe. This process of eternal recurrence could imply that every event, from the formation of galaxies to the birth of stars and even the evolution of life, might have happened countless times before and will happen countless times again in the future. The universe, in this view, is not just a fleeting moment in the vastness of time, but part of an eternal cycle of creation, destruction, and rebirth. A significant challenge to the cyclic universe theory comes from the current observations of dark energy, a mysterious force that is driving the accelerated expansion of the universe. According to standard cosmology, the presence of dark energy suggests that the universe will continue expanding indefinitely, eventually reaching a state of maximum entropy where no further work can be done, known as the heat death. In this scenario, the universe would continue expanding forever and no future Big Crunch could occur. However, some versions of the cyclic universe theory account for dark energy by proposing that its effects are only temporary. In these models, dark energy would eventually decay or transform, allowing the gravitational forces of matter to reverse the expansion and trigger a new cycle of contraction. One such model, known as the ekpyrotic universe, builds on the idea of a cyclic universe but incorporates recent developments in string theory and quantum gravity. In this theory, our universe is part of a higher dimensional structure called a brane, which exists within a larger multidimensional space known as the bulk. Periodically, our brane collides with another parallel brane, and this collision produces the energy required for a new Big Bang. After the collision, the universe expands for a time, before eventually contracting again as the branes move toward each other for the next collision. This theory provides a possible explanation for how cyclic events could occur even in the presence of dark energy, as the universe's cycles are driven by interactions in higher dimensions rather than purely by gravitational forces. The hidden force drawing galaxies. Located roughly 150 to 250 million light-years from Earth, this massive region of space is pulling entire galaxies, including our own Milky Way, toward it at astonishing speeds of up to 600 kilometers per second. The Great Attractor appears to exert an irresistible force on a large portion of the universe, drawing galaxies across vast distances in its direction, yet much about its nature remains shrouded in mystery. What lies at the heart of this gravitational anomaly? What is the force that seems to be pulling entire galactic superclusters toward a region of space that is, to a large extent, hidden from view? The discovery of the Great Attractor emerged from observations of how galaxies within the Laniakea supercluster, the vast collection of galaxies to which the Milky Way belongs, were behaving. Rather than expanding uniformly as predicted by the standard model of cosmic expansion, these galaxies were exhibiting peculiar velocities, meaning they were moving toward something rather than merely being carried along by the expansion of space. This was an unexpected anomaly, given that, in a universe driven by expansion since the Big Bang, most galaxies should be moving away from one another. By measuring the motion of galaxies within the supercluster and their redshifts, which indicate how fast an object is moving away or toward an observer, scientists determined that something was pulling the galaxies in a specific direction. This led to the realization that there was a massive gravitational anomaly, something incredibly dense yet hidden from view, exerting its influence over a vast area of space. This phenomenon was dubbed the Great Attractor. However, one of the major challenges in studying the Great Attractor is its location. It lies in a region of the sky known as the Zone of Avoidance, which is heavily obscured by the Milky Way's plane, making it difficult for optical telescopes to observe. The dense gas, dust, and stars of our own galaxy block much of the light from objects beyond it, complicating efforts to directly study the area where the Great Attractor lies. Despite this, through indirect observations such as radio waves and X-rays that can penetrate the Milky Way's plane, scientists have been able to glean some information about the region. The central mystery of the Great Attractor lies in what it contains, and what is producing the immense gravitational pull drawing so many galaxies toward it. Several hypotheses have been proposed over the years, with one of the most widely accepted explanations being that the Great Attractor is the result of multiple large clusters of galaxies concentrated in a relatively small region of space. These galaxy clusters, such as the Norma cluster, contain thousands of galaxies and massive amounts of dark matter, which together generate a significant gravitational field. This gravitational field is powerful enough to pull nearby galaxies and superclusters toward the region, acting like a cosmic anchor in the structure of the universe. The role of dark matter in the Great Attractor's influence is particularly intriguing. Dark matter is a form of matter that does not interact with light or other electromagnetic radiation, making it invisible to traditional telescopes. Despite its elusive nature, dark matter is believed to make up about 85% of the universe's total matter content. Its presence is inferred through its gravitational effects, and it plays a crucial role in holding galaxies and clusters together. In the case of the Great Attractor, a substantial amount of dark matter could be contributing to its gravitational pull, forming a hidden mass that we cannot directly observe, but which shapes the movements of galaxies on a massive scale. Another possibility is that the Great Attractor may be part of an even larger structure, such as the Shapley supercluster, located beyond the Great Attractor itself. The Shapley supercluster is one of the largest known concentrations of galaxies in the universe and lies roughly 650 million light-years away. Some scientists propose that the Great Attractor may not be the ultimate gravitational center, but rather one part of a much larger web of gravitational forces that includes even more massive superclusters beyond it. This suggests that the Great Attractor could be just one node in a vast cosmic network, all of which contributes to the large-scale structure and motion of galaxies across the universe. Central black hole theory. This theoretical black hole would exert an immense gravitational pull, influencing the movement of galaxies and cosmic structures on a vast scale. While there is no direct evidence of a singular black hole sitting at the heart of the universe, the notion raises intriguing questions about how the universe is structured and what forces might be guiding the movement of galaxies and superclusters. Supermassive black holes are already known to exist at the centers of most, if not all, galaxies, including our own Milky Way, where Sagittarius A*, a supermassive black hole with a mass around 4 million times that of the Sun, resides. These black holes act as gravitational hubs, pulling in gas, dust, stars, and even entire star systems. Their gravitational influence shapes the orbits of stars and regulates the activity of their host galaxies. It stands to reason that if smaller-scale structures like galaxies are anchored by supermassive black holes, then perhaps on larger scales, there could be even more massive black holes exerting a similar gravitational influence over clusters of galaxies or even entire regions of the universe. The idea of a central black hole at the universe's core could also be linked to theories of how large-scale structures like galaxies and clusters form and evolve. If such a black hole existed, it would act as a kind of cosmic anchor, pulling surrounding matter toward it and possibly influencing the formation of the cosmic web, the network of galaxies and dark matter that spans the universe. The gravitational pull of this hypothetical black hole could shape the motion of galaxies and superclusters, creating the large-scale flows and movements observed in the universe today. In this theoretical scenario, the central black hole would be vastly larger than any supermassive black hole we've detected so far. For instance, the largest black holes we know of, such as Ton 618, which has a mass of around 66 billion times that of the Sun, pale in comparison to what might be required for a central black hole anchoring the universe. This black hole, if it exists, could have a mass many orders of magnitude greater, perhaps even surpassing trillions of solar masses. Such a black hole would not just be a gravitational anomaly, but a dominant force shaping the structure and evolution of the entire cosmos. One of the key challenges in exploring this idea is the fact that the universe does not appear to have a central point in the traditional sense. The cosmological principle, which underpins much of modern cosmology, suggests that the universe is homogeneous and isotropic on large scales, meaning that it looks the same in all directions and has no preferred location. This principle implies that there is no singular center of the universe, as it is expanding uniformly in every direction from every point. In this view, there cannot be a central black hole acting as the core of the entire universe, because there is no universal center. However, while the idea of a central black hole for the entire universe may be at odds with the standard cosmological model, there remains the possibility of localized regions where a supermassive black hole plays a dominant gravitational role. For example, in a supercluster of galaxies, a particularly massive black hole might exist at the center of the cluster, influencing the motion of galaxies and cosmic material in the region. This could mirror the way individual galaxies are governed by the gravitational pull of their central supermassive black holes. The concept of a gravitational anchor becomes more plausible when applied to smaller, though still massive, regions like galaxy clusters or superclusters. The idea that a black hole of unprecedented size could lie at the center of a supercluster or another large-scale structure in the cosmic web is not entirely implausible. The gravitational effects of such a black hole could help explain certain anomalies in galactic motion, such as peculiar velocities, where galaxies appear to be moving in ways that are not entirely explained by the universe's expansion. A hidden supermassive black hole could be exerting a force on these galaxies, subtly guiding their movements. But how could we detect such a black hole if it exists? The first step would be to observe the gravitational effects it exerts on its surroundings. Just as the presence of black holes in galaxies is inferred from the motion of stars and gas orbiting them, a central black hole in a supercluster or larger region of the universe would leave a gravitational imprint on the motion of galaxies. If we observed galaxies moving toward a specific region in a way that could not be explained solely by the expansion of the universe or known gravitational sources, this could indicate the presence of a massive unseen object, a potential supermassive black hole. Astronomers already use redshift and blueshift measurements to determine how galaxies move relative to us, with redshift indicating that an object is moving away and blueshift indicating that it is moving toward us. By carefully studying the motions of galaxies in superclusters, we might detect a pattern that suggests a common point of attraction, one that could hint at the presence of a central black hole. Another method involves using gravitational lensing, a phenomenon where the intense gravity of a massive object, such as a black hole, bends the light from objects behind it. This distortion can reveal the presence of the black hole even if it cannot be seen directly. If a supermassive black hole larger than any previously observed lies at the core of a supercluster or region of the universe, it would also likely be associated with high-energy phenomena. For instance, accretion disks, the swirling disks of gas and dust that form around black holes, are known to emit tremendous amounts of X-rays and gamma rays as the material is accelerated to near-light speeds before falling into the black hole. Observing such high-energy emissions in a region where no black hole is visibly present could be another clue that a hidden supermassive black hole is lurking. Where is the center of the universe? The question of where the center of the universe is might seem like a straightforward one. After all, when we think of things expanding, like a balloon or an explosion, we imagine there must be a center point from which everything is moving outward. But when it comes to the universe, things aren't quite that simple. In fact, the idea of a center doesn't really apply in the way we usually think about it. To understand why, we need to dive into how the universe actually expands and what that means for our understanding of space itself. Let's start with the Big Bang, the event that gave birth to the universe around 13.8 billion years ago. Many people think of the Big Bang as an explosion, something like a firework, with matter flung out from a single point, expanding into empty space. But that's not what happened. The Big Bang wasn't an explosion in space, it was an expansion of space itself. Imagine space as the surface of a balloon. As you blow up the balloon, every point on the surface gets farther away from every other point. But the balloon's surface doesn't have a center. There's no specific spot that you could call the starting point of the expansion. The same is true for the universe. In the Big Bang, space didn't expand from a central location outward. Rather, space itself began to stretch, with galaxies moving away from each other as space expanded between them. This means that every point in the universe is moving away from every other point, but no single point is the center. It's a hard idea to wrap our heads around because we're so used to thinking in terms of objects moving in space, but in the case of the universe, it's the space itself that's expanding. To add to that, we have the idea of cosmic homogeneity, the notion that the universe looks roughly the same in every direction, no matter where you are. This is one of the key principles of cosmology, and it's backed up by observations. When astronomers look at the universe on a large scale, they see that it's fairly uniform. There are galaxies and clusters of galaxies spread throughout space, but on the biggest scales, everything is distributed evenly. Because of this, there's no special location or direction in the universe. Every region of space is pretty much like every other region, and that means there's no center to speak of. It's natural to think that if the universe is expanding, it must be expanding into something, right? After all, when you blow up a balloon, it expands into the air around it. But here's where things get tricky. The universe isn't expanding into anything. The universe is everything. There's no outside of it that it's expanding into. When we talk about the universe expanding, we're talking about space itself stretching. It's not like a balloon expanding into the room, it's more like the surface of the balloon expanding, but with no need for anything outside of it. The space between galaxies is increasing, but there's no edge or center in the way we'd normally imagine. A lot of misconceptions come from trying to picture the universe in terms of everyday experiences. It's tempting to imagine the universe as a huge explosion where everything flies away from a central point, but this just doesn't match what we know from modern cosmology. In fact, if you were to choose any galaxy in the universe, you'd see all the other galaxies moving away from you. This happens no matter where you are in the universe because, again, the expansion of the universe is happening everywhere, not from a central point. Another key to understanding why there's no center is to think about the idea of the observable universe. The observable universe is the part of the universe we can see, the region from which light has had time to reach us since the beginning of the universe. But here's the catch. Every observer, no matter where they are in the universe, has their own observable universe. So from our perspective on Earth, it might look like we're at the center of the universe because everything we can see is expanding outward from us. But if you were in a distant galaxy billions of light years away, you'd also think you were at the center of the universe because you'd see the same thing, all galaxies moving away from you. This leads to an interesting realization. The universe looks like it's expanding from every point because there's no preferred location in space. The observable universe is just a small fraction of the entire universe, which is much larger than what we can see. And the fact that every observer has their own observable universe means that there's no single cosmic center. Each observer is essentially at the center of their own bubble of the universe, but that doesn't mean the universe itself has a true center. To make this clearer, let's go back to our balloon analogy. Imagine you're a tiny ant on the surface of a balloon. As the balloon inflates, you see every other ant on the surface moving away from you. From your perspective, it looks like you're at the center of the expansion. But if you were to ask one of the other ants, they'd say the same thing, that all the other ants are moving away from them. No single ant can claim to be at the center because the expansion is happening everywhere on the balloon's surface at the same time. The universe works in a similar way. No matter where you are, it seems like everything is moving away from you. But that doesn't mean you're at the center of the universe. What makes all of this even more fascinating is the realization that the universe could be infinite, or at least much larger than what we can observe. If the universe is infinite, there can't be a center because an infinite space doesn't have a middle. And even if the universe isn't truly infinite, it's still expanding in a way that doesn't create a central point. Instead, the expansion is happening uniformly across all of space. The bottom line is that the universe doesn't have a center in the way we're used to thinking about centers. The expansion of the universe isn't like a balloon popping from a single point, but more like space itself, stretching uniformly, carrying galaxies along with it. This expansion happens everywhere, and because of the uniformity of the universe, no spot is more special than any other. The observable universe might look like it has a center from where we stand, but that's just because we can only see so far. In the grand scale of things, every point in the universe is just as much a part of the expansion as any other. The idea of a center doesn't apply to a universe that's expanding everywhere at once. As we've seen, the universe doesn't have a central point. Its expansion is happening everywhere at once, uniformly stretching space in all directions. The universe, on the grandest scales, appears isotropic, meaning that it should look the same in every direction. This idea forms one of the cornerstones of modern cosmology, providing a stable framework for understanding the universe's large-scale structure. But as is often the case with scientific discovery, nature sometimes surprises us, revealing complexities we hadn't anticipated. I hope you enjoyed the video. If you did, feel free to subscribe to the channel. Thanks for watching.